thank you very much for the invitation too. This is a project that was started with Alison Etheridge some years ago, with a big pause in between, and now a collaboration with Bastian. So I'm very glad that I can present the subject because, I mean, some of you might have heard about these different models of population genetics. We've got the Moran model, we've got the Fleming-Viot model, the Wright-Fisher diffusion, Wright-Fisher model. We've got this entire class of different models. And one thing that they all have in common is that they have this very strong assumption that the population size is constant in time. And if you look at, for example, the spatial number Fleming-Viot process, it's also constant in space. And so the aim of this project is to try to break down this assumption and try to modify these classical models to get a new one that incorporates variation in population size, but is still tractable analytically so that we can still get some results. And so today I'm trying to present to you how we can do this, or what we try to do this, where are the challenges, what we can already do, and yeah, all of this. So I will start with the classical models, so just the Fleming-Viot process. And we've got a bit of an insight already yesterday, but from a different angle. So there we saw the Moran approximation of the Fleming-Viot model. Today I'll take a bit of a different approach. Okay, so let's start. When you want to think about the Fleming-Viot model as an individual-based model, what you can do is that you consider a population, say of two types. So you've got some individuals, and some of them are black, and the others are, let's say, red. I hope you can see this. Okay. And now from time to time, there will be what is called a reproduction event, and this will affect all individuals, and there will be 3 steps in each reproduction event. The first thing that we do is we choose a parent. And we choose a parent uniformly at random from the population. We say we chose this red individual. Then the next step is that there will be some deaths. Okay? Which is simply a thinning of the population, meaning that every individual in the population has the same probability to die with probability u and independently of the others. So, for example, let's say this one dies, this one dies, this one dies, and perhaps the parent also dies. Okay, so the parent is not protected from dying. It may die, it may not die. And then the last step is adding offspring. And as expected, the offspring will have the same type as the parent. So we've got some new individuals added back into the population, but all of them are of type red. So, now the question, and which I haven't answered yet, is how many offspring should we add to make sense of, or to get a sense of a model. And to understand or to think of the best choice, let's think about this thinning. This thinning means that we kill a binomial number of individuals in the population. Okay, and let's say we have approximately n individuals in this population, then we should kill about binomial nu individuals in the population. And the nice thing about the binomial distribution, when we think about having a large number of individuals, is that we have a concentration happening, that this can be approximated by its mean, and then some lower order terms. And we always think about infinite population limits, and in those infinite population limits, to make sense of them, we rescale by our scaling parameter, our initial number of individuals, meaning that this fluctuation doesn't happen at our scale. We don't see it. Okay? So what we just see is we kill a proportion u of the population every time. And so what is done classically is to balance these deaths and add in another u to the population to have this nice balance. And so what is often done is we take a Poisson number of offspring. Because Poisson, the distribution has the exact same property. We have the mean and then plus minus some order terms. Okay. So now we've got this classical individual-based model, and when we take this infinite population limit by rescaling, as I said, we forget about the fluctuations, we forget about this n here, and so what we get is killer proportion u, add u in. So the total population process in the limit should behave like this. When there's an event, I kill a proportion u of the population, and then I add back u individuals. Oh. Okay. And now we start with little n individuals. So in the scaling limit, we start with n0 equal 1 as a total population, which is a fixed point of this evolution equation, and that means that our total population size is simply constant equal to 1. That simplifies things a lot, okay? Because now we only, if we want to understand the evolution of this red subpopulation, we don't need to care at all about the entire population because we know that's constant. So when I just consider the subpopulation of red individuals, then I would expect the following evolution. When there's an event, I kill a proportion u of the subpopulation, okay? Because the deaths don't distinguish between types. And then there are two possibilities. I add offspring if the parent is red, and I add nothing else. I hope you can see this with this. Yeah. Okay. And so that means that in the evolution of the subpopulation, I actually see something. And that is what the classical Fleming-Viot process is all about. Is this understanding this process. Now, I will use from now on a lot of generators for Markov processes, but don't worry, I will stay at a high level and try to explain what those generators mean. So I hope that even though some of you may not be super familiar with generator handling, it might be understandable. And so this process X, okay, is describing the subpopulation. That's a Markov process. And the generator is given like so. There are two possibilities. If I choose the parent of type red, which happens with probability x over n being constant, just with probability x, then I see both the killing and adding in the offspring. And if on the other hand I choose the wrong parent, then the subpopulation only sees the death and not the offspring. Okay. Now, there's one parameter that I didn't speak about a lot, which is this u, okay? And this u we might take any value between 0 and 1. And it's called the impact parameter because it controls how much one singular event impacts the population. Okay, so if u is very close to 1, I replace the entire population, whereas if u is very close to 0, the fraction of the population that is replaced is extremely small. And so one very natural question is to ask, what happens if u becomes very small? The impact becomes small, so I shouldn't see a lot of evolution going on, but what exactly am I seeing? And that's another theme of this talk, where we do a lot of Taylor expansions. So if I use Taylor here for the regime u being very small, right? then I tailor x, the zeroth order just goes away, which is very nice. And so I'm left with 1 minus x u f prime of x plus 1 minus x squared u squared f double prime of x. And for the other case, I'm left with xu f prime of x and x squared u squared second derivative. Okay. So I don't even mention the lower order term, but the higher order terms, because they will just go away. And I forgot a minus here. And so there's a reason why I chose the second order, because the very nice thing about this model is that the first order will go away. Okay, so we've got a x1 minus x here, we've got a x1 minus x here and a minus, and so this first order just goes away. Okay. And this is something very important because it will be different in what we see in the second half of the presentation, and means that the balance between birth and death is so perfect that we don't see fluctuations. We only see the second order fluctuations. And so what is left here is a term in u squared, and you may or may not want to believe me that this is actually just x, 1 minus x, and second derivative of x if you compute that. Okay. So now what does that mean? So there are three things we need to worry about. The first thing is the second derivative. Second derivative means there's a diffusion part. Diffusion part means in the stochastic setting there's a Brownian motion. Then the second thing is here, in front of the diffusion part, that's the variance of my Brownian motion. And the third part is this u squared, saying that the effect that I see is proportional to u squared. So if I want to see an evolution, the right time scale I need to look at is actually 1 over u squared. Okay? If I look at the time scale 1 over u squared, this goes away, and we see this. Okay? And those familiar with the model see that this is just a generator of the Wright-Fisher diffusion. So this is just the generator of okay, so that's very nice because now we've already connected two of the classical models. Now we go on further because now we can define the so-called lambda Fleming-Viot process, where we take the Fleming-Viot process, but we're allowed to take the impact randomly. Okay? So we take some probability measure on 0, 1, call it lambda because that's the name of the process, and then we've got a new generator. Which says, okay, inside I will just have the evolution that we just saw, but we picked this parameter randomly with this distribution lambda, which is the finite measure on 0, 1, and we've seen that the right way to scale it is to divide by u squared, which is also the reason why yesterday we had this rescaled Poisson measure. And so now that we have this model, there are a lot of interesting questions you want to ask, which might be, is there anything which is some sort of duality? So is there a dual process? What is the duality function, etc.? There is the question about space. There was a lot of recent research in the last decade because it turns out that the spatial variant of this model is extremely nice, or behaves well enough to understand behavior in space and gives nice results in space. There's the question of fixation. Does one type fixates when I take time to infinity, etc. Okay, so that's things that I will not talk about. Instead, we'll go back to the drawing board and try to see where can we add fluctuating population size. And again, if there are any questions, just feel free to ask. Okay, so in the first 2 points here, there's nothing that we can do. That's just the very natural things to do. Yes?
And should we understand what represents the lambda, the process lambda?
The lambda says, for example, if you take the Dirac function, that is just what we had before. But if you take, say, a probability distribution on 0, 1, then this says how you take at random your impact Q. Okay? And yeah, and then you can take any finite measure, which is just a time scale of the time change of the process. Yeah, so these two first points, there's nothing that we would change because those are very natural. For the last one, the only motivation that I had for you is, oh, it cancelled out, so we take it. Okay. That's perhaps not the best motivation for definition. So instead, the idea is, okay, what happens if we take some other distribution? Just anything. So instead of the Poissonian, we just take some random variable psi un. And the only very important thing is, if we want to have a somehow constant population size, because we want to look at large time scales, we don't want them to die out or to explode, the only sensible thing is to do in mean, we should have this property. Meaning that we have balance in mean, but we allow for some fluctuations. It may be a lot smaller, it may be a lot larger. Okay. And if we have that, so that's like the main difference from the previous model. Instead of just taking Poissonian, we allow for a lot more different offspring distributions. And this one I'll go through. If we have this and we have some suitable convergence of these random variables to some limiting random variable, then in the killing nothing has changed, and only in the offspring distribution we see some random variable psi u. And here, coming from this condition that we had, what we get is that in mean we stay in the old regime, in the balanced regime. And now this is wrong. Okay, so 1 is not a fixed point anymore. At every event I may add a random number of offspring, not necessarily 1. So we shouldn't expect it to be constant. And for the subpopulation process, the same thing. If the parent is of the right type, we add the offspring. If it isn't, we add nothing. And that's already one of the crucial differences. X is not the proportion of red individuals anymore. It was before, because n was constantly equal to 1. Now it's not. Now it's just the subpopulation process. And if we want to have the proportion process, we actually need to divide. Okay. And that's bad, because imagine that for a long time we don't have any offspring, then our population decreases nearly to 0, and then it behaves very badly. So that's not nice, but we have to deal with it. Okay. So now we play the same game as before. So first thing is that it's not a Markov process anymore. Okay? The subpopulation process really depends on the total population process, because the parent is red with probability x over n. So instead, we will need to look at the pair of the processes. Okay. This makes things a bit more hairy, and I will have to clean the board first. So if there are any questions, that's the perfect moment. So as you can see, that the theme is that the processes or the ideas remain very similar, but it turns out that there are some major difficulties coming. adding to the ones that we had before. Now that we have to keep track on both the subpopulation and the total population process is one, and having this fraction is another. That will be very annoying later on. Okay, let's start with an easier process, okay? Even though X is not a marked process, N in itself is marked one. Right? And its generator is extremely easy. That's just saying at every event we will kill a proportion U and then add the offspring. For NT-XT, we will have a double generator, which is a bit annoying, so I will make my life a bit easier and at least here suppress the dependence in N, but keep in track that alone in itself it's not Markov. So here we've got the same procedure as every year. If the parent has the right type, which happens with probability X over N, then I add the offspring. And if it's not, then we go. I will not write down the generator of the proportion process because it is horrible. Later on we will need the generator for the proportion process, but in a very special case in which it takes an easier form. So I prefer to work with those two processes instead. And so what we did with the classical model first was take the small impact regime, trying to understand what happens when U goes to 0. And you kind of already see the problem, right? This thing is large, or can be very large. That's the main idea of this model. And that means that we cannot use Taylor anymore. But we try anyway. So let's take the easier of the two generators to use Taylor. So U becomes small. At first we keep it inside, so that we perform Taylor around N plus psi U. Now, this is already something. I mean, that's better than nothing. So we have the time scale 1 over U in some sense for the second term, but we still have to manage this minus that. Okay, so let's take another. So what we have is this term minus U and expectation of F prime N plus psi U. And then we've got the second term. Okay, so two things. We had this condition that the expectation of psi U is U, right? So an expectation is balanced. That means when we take U to 0, psi U will also converge to 0 in some sense. So this term, that's just approximately F prime of N. Okay. So this first term, we can understand it as being U for the time scale and being some sort of exponential drift to 0. For the second term, it's a bit more complicated. So some of you may recognize some sort of jump structure, so we jump like psi u. Now imagine we can use Taylor, meaning that this is somehow f prime of psi u times f prime of n. Okay. Then this would be expectation of psi u times f prime of n. If we could use Taylor, which we can't. And so the right condition to impose on this thing here, this being of order u2, right? This is u. So we should expect this also to be of order u somehow. So this u time seems to be the right time scale. Okay, so the right condition on this is to converge to something. And this will have a very specific form that I will put here, so that I have some space left on the other side. This will converge to something which will be a sort of decomposition in two things. First, this classical part, where we assume psi u to be small enough to do Taylor. And the second one, which handles the jumps that are so large that we still see them in the limit. And this is what I will call the Levy condition. That's not something that is used in literature, but just to give names so that we can refer to it. What we do is for functions that are 0 at the origin, we'll ask that the limit as u goes to 0 of 1 over u, expectation of g of psi u is gamma u prime of 0, and then so why would that be like a sensible definition? So first thing to note is somehow that's a better control on psi u. So we had this very coarse control saying that the mean is u. But instead now we have to control all moments in some sense of u, or yes.
So is the right interpretation is that the impact that you have, or the reproduction that you have, is a Levy process with respect to u dm?
Yeah, will be, exactly. So there it's just a jump process. But when we take the limit, and this measure here will be a Levy jump measure, and we get a jump process. Okay. Was it the question? And so we've got here the classical part. That's the one where we can use Taylor, okay? And that's only valid for a portion of our random variable. And this other portion, which is large, will be translated into Levy jump process. It's super hard, isn't it? Okay, so if I use this, what I get is the gamma going into the drift, and then some jump part. Okay, for those familiar with jump processes, if you don't see the compensator, that's just because all of our jumps are positive. So there's no need for a compensator. Okay, so now this constant drift, this classical part, which in the classical model will be 1 because the entire offspring goes into this classical part, means that we would have a drift to 1, and that means we have this constant population size. That is what's broken down here. So gamma might be smaller than 1 or even equal to 0. And then we have additional jumps distributed with respect to some Levy measure. Okay, and important thing, the time scale is really 1 over u. That is perhaps not super surprising because we don't have any Brownian part in it anymore because only first order Taylor. But on the other hand, it's super interesting because it means that this small change makes this model work on a completely different time scale than the classical model. So, yeah. Right. You can do the same thing for the process n and x. What we get is, okay, I will write it down, it's not super surprising. It's the same scheme as before. The jumps will only apply if the parent has the right type. And the drift also, this gamma will also only apply if the parent doing the reproduction event is of the right type.
Excuse me.
Yes.
So there you got the f prime of n plus cu, right? I was just wondering why you should say that is close to f prime n if you have the Levy condition. Because you could potentially do a second order Taylor. And then...
Yes, there's one over u there, right? So, there's one over u already cancels here. So with the Levy condition, what you would... Okay, so first thing, the Levy condition doesn't really apply because that only works for functions which are 0 and 0. And the second thing to note is, okay, so if I look at the right time scale, it's just this u that goes away. So I'm looking at this. And now this psi u has mean u. So it converges to 0 anyway. And so if it converges to 0, this part just converges to this. So this
right,
is
simply by continuity of f prime at n.
Yeah, and so you can use the Levy condition to actually show this.
Okay.
But yeah.
Okay, cool.
Okay, so the generators. So now we are at the regime of what would correspond to the Wright-Fisher diffusion. Yes.
One question. So your Levy measure is it really a Levy measure? So can you have a singularity of order 2 or only of order 1?
Of order 1, because
order
it's
1.
a positive Levy measure.
This
So
is
it's the Levy measure of the Levy subordinator. So the condition is that 1 sub x psi.
Right.
That is finite. It's finite. And also, the second thing is from a biological perspective, as I said, what we're looking for, from a modeling perspective, let's say, what we're looking at is those psi-u's having mean 1. And so we would expect that gamma plus the mean of psi is equal to 1. With the extreme case, classical gamma is equal to 1, and in other extreme case, no positive drift, only jumps. With expected jumps a bit more. Yeah, it's a bit more subtle because these Levy jump measures can be very nasty. You can have infinitely many microscopic jumps. I will not go into these details, so you can think of this as the expected jump size. Good. The generators. So what we would have is gamma psi. So for n, this, let's just do it for n. We've got the exponential drift to gamma. Then we've got the same exponential drift, but only at rate x over n. And then we've got the jumps, and again we've got these x over n, then the integral, and 1 minus x over n, and the integral, where the total population process always sees the jump. Sorry, it was pre-limit. And the subpopulation only sees the jump when the parent having the right factor. And now we can all rejoice because now we can write down the generator of the proportion process without too much pain. And it's actually quite elegant in some sense. So first thing is this exponential drift actually completely disappears. So we don't see the exponential drift because it occurs both there and both there with the v here, so it just cancels out. So we don't care about this jump measure in some sense. Again, I suppress the dependence in n on the left hand side. And so what we see is just, okay, I already write it and put these integrals together for a reason that we will see in a second. So w times f of 1 minus psi over n plus psi, w plus psi over n plus psi, yes, that's w, plus okay. Now the nice thing is that this is just the generator of the Fleming-Viot process with a very special impact. So we can rewrite this. Where should I put it? I guess there. With the generator of the Fleming-Viot process with impact psi over n plus psi. Why? I don't know. Perhaps there's some intuition that we can get with further work, and perhaps we've done some insight, but that's what it is. The proportion process of this limiting process that we got Levy evolution process, lack of a better name, is described by some sort of averaging of the Fleming-Viot process with special impacts. Okay, so now we have constructed our model and we've got some time left. Very nice. So we've got the same question: can we extend it to space? Yes, we can. So, like for the lambda Fleming-Viot process, we can do a similar thing in space. It becomes a lot more hairy than without space, so I will stick with the non-spatial thing. The second thing is, and which is somehow intriguing, is in the modeling assumptions that I had, I just copied the Fleming-Viot process, right, step by step, and just exchange one thing. But when you think about it a bit more, and you have a population that varies in size, then it is quite natural to assume that the speed at which the population evolves depends on the population size. So, for example, if the population is very large, you expect there to be more deaths, more births, whereas if the population is smaller, perhaps there are less births, less deaths. And so you can do this by changing the generator by just making a time change in the model. That's why we'll not talk about it a lot, because in a non-spatial case, it's actually the same. So you just perform a time change and then you're fine. In space, on the other hand, it's extremely interesting to look at this, because then you would need to perform a different time change at every point in space. And there is a way to write down a generator which heuristically does this, okay? And this process exists and everything is fine. But when you try to do analysis on it, it becomes extremely difficult. So you cannot do a time change anymore. And this time change version actually has some very weird properties. So so instead of that, which all sounds super interesting, I hope so, be teased. Instead of that, we're looking at two other properties of this model. The first one is, what is the relation to the classical model? Because what we would like to have is that it is some sort of extension of the classical model. Okay? And to do that, you want to have our first result saying, when the jump vanish, in a sense that I will say in a moment, then this process NW of the Levy evolution process, so I'm looking at this and this, actually converges to just one, because in the classical setting, no evolution in the total population process, and the Wright-Fisher diffusion. So that's and it doesn't matter if you take W or X, it's all the same. So that's already a very nice result saying, okay, we actually have this sort of continuity. This really can be interpreted as being an extension of the classical model. And the second, I call it result, is concerning duality, right? What we would like to have is some duality, if everything works fine, moment duality, because it gives you a lot of information. And when you have a look at this generator, it's just a Fleming-Viot generator. And the Fleming-Viot has moment duality. So you would hope that moment duality is a thing here. It's actually not difficult to write down a candidate for the dual process, and we've done some simulation which show that there is duality. So there's agreement between the two quantities that are important in duality. We're trying to prove it, and we're close, but it's not a result yet, I would say. Okay, so let's focus on the first one in the remaining time. Okay, so there are two problems to solve. First one is the total population process, and then second, the proportion process. And I will turn around and start with the easier one, with the proportion process, and just assume that we've shown the first part. Okay, so we assume that n goes to 1 in a sufficiently well-behaved way. And that means that in this generator, right there, of the proportion process, we can simply replace our n by 1. And actually, that is this first step that I just did is probably the most delicate step in the proof, because this is where this x over n comes into play. So we have to make sure that n doesn't go too close to 0, which can be a problem. Okay, so but let's assume that's true somehow, approximately. Then we can just use all the machinery that we had before and say, well, that's nothing else than this factor squared times the Wright-Fisher diffusion generator. This is what we had for the Fleming-Viot type process, which you just put outside. And so what we really have, and I will write in a bit of a sloppy way, is the mean of this quantity with respect to the psi measure. And so it turns out that if this goes to 0, then we can rescale time by this quantity and we get Wright-Fisher diffusion. So now we only have to show that we can actually replace this. And so here, if I look at the generator for the total population process, there are two parts, right? There's this drift part, and then we have the jump part. Now, let's look at the jump part. Again, we just assume that we can use Taylor. In this case, this is just f psi f prime of n plus psi squared f double prime. And we already know that we rescale time by this factor, right? This behaves in the same way as psi squared. So we will see this term here. That's fine. And this term, since the square goes to 0, psi itself will go to 0 too. So even faster. So we will not see the first term. So what we expect to see is that these jumps will give us standard Brownian motion, or perhaps rescaled Brownian motion, something like this. So what about this term? If we didn't have it, as I said, we would see something like this, which would be very bad when we touch 0. We want to stay at 1. And the thing is, okay, so I lied a little bit. This part here actually goes in here and becomes 1. Okay, that's a bit magic, but you can trust me, it does. And so what we really see is it drifts towards 1 instead of gamma. And when we rescale time by something, this drift becomes very large, because there's nothing that goes to 0, right? So what we see is a Brownian motion which is forced more and more and more and more towards 1. And so the limit, this motion, this Brownian motion is dominated by this drift, and we see constant population size. Okay.
So again, why is it that that term goes in there?
Okay, so yeah, that was not correct what I wrote there. Okay, so we've got this psi f prime of n. Shouldn't have said it goes to 0, it doesn't. I don't know why I said it. No, that was from this assumption there. gamma plus the mean of xi
Yeah.
is equal to 1. And then we just sum it up.
Ah, okay, yeah.
And then it's fine. So this goes into here.
Okay, no, thanks.
Yeah, my mistake, sorry. And so that's fine. We can prove this convergence. Turns out to replace this convergence is not enough. Because what we do there is we prove convergence in law, and it still might be that at some very rare event we come very close to 0. So instead what we need to control, it turns out, is the expectation of the square of the supremum norm. Okay. And so right now we have this additional technical assumption in our theorem saying that this is bounded. But we hope that we can remove this additional. I think it should be possible to prove this from here. But yeah, that's for the future, I think. Okay, so a few words for duality. So the main problem with duality is what we really want to have is this moment duality, where we say that if we start with some proportion of the individuals and take it to the power nt, where nt is the dual process, then this is the same as looking at the evolved form of the proportion process and looking at the beginning. So, and usually this is some sort of number of lineages, similarly as we heard yesterday afternoon, of some sort of coalescence. In the lambda Fleming-Viot process case, this is the lambda coalescent. In the Wright-Fisher diffusion, it's just the Kingman's coalescent. Now we've got this very special, very particular form of our proportion process. So this is very similar in some sense to a lambda Fleming-Viot process, okay? With this exception that we have this n dependency. And so what we expect to see is actually a lambda Fleming-Viot process, but where the rates depend on the total population size. And to make this work, the main ingredient in there is to say, okay, usually when we do this sort of stuff, what we can do is just take two different processes. We take the forward in time process, and then separately we define the backward in time process, and then everything works out because generators are nice. In our case, we can't do that. So what we need to do is we've got we've got this population process which might do this somehow. Okay. Jumps and exponential decay. And then we actually have to use the backwards in time total population process. And on this, above this backwards in time process, we define a coalescent, or we define this number of lineages process, which is just a pure depth process, saying that at every jump event, and there might be a lot of them depending on this measured psi, on every of these jump events, we may have a coalescence event. So there is no coalescence on these intermediate steps because those events are too small to be seen at our time scale. And instead we see only coalescence at these big jumps, which happens, and the coalescence probability is proportional to the jump size divided by the total population size. And and so at the moment we're looking at finishing the proof, and we're quite confident that this should work out fine. Yeah, thank you very much.